Before we do, let's take a moment. Hopefully you all had a nice 3-day weekend. Let's see. Who's missing besides Surratt? Who sits next to you?
No one, there's no
Person's next. Got it. All right. If you take a look at where we are right now in the course, we have finished 2 blocks of the convection. We have finished the introductory theoretical, which started off with a massive PowerPoint slide of all of them, governing equations and how they can be used, ending up with the Reynolds analogy. Then we moved into the Blasius solution. That was external flow over a flat plate. And then we moved on from the Blasius solution, which is a classic solution, to the rest of the empirical formulations in Chapter 7, which is external flow over flat plates, geometries, and spheres. Okay? And so we concluded that last time. And now we begin Chapter 8, which is the 3rd chapter in the convection block, and which focuses on internal flows. And internal flows are flows through pipes and tubes. And so with that, let's begin. We'll begin by taking a look at laminar flow in tubes, the hydrodynamic considerations. Let's begin with a tube, or a pipe. So, there's a tube. And we have some flow. This will be our u direction, the x-axis, and it will be r will be in this direction. And we'll have some u infinity. That is the flow entering the pipe. Okay? Now what happens when the flow enters the pipe? What? Very good. Just stop right there. The boundary layer begins to build. Some of the fluid adheres to the surface of the pipe, and then other molecules are slowed down as they adhere to the ones that are stuck to the surface of the pipe, and so on and so forth until the boundary layer builds. So what we see is, if we look at this in 2 dimensions, is the boundary layer begins to build like this. And it begins to build all the way around the pipe. And so in this area here, where the boundary layer is not complete, it looks something like this. In the center here, where the flow has not been influenced by the formation of the boundary layer, it's still u infinity. But elsewhere, it has begun to slow down. We speak of this area here as the entry region. and it's known as XFH. That is the hydrodynamic entry region. This is the hydrodynamic entry region, and this is the hydrodynamic entry length. Okay, the hydrodynamic entry length. Now, what happens as we reach down here, where the boundary layer is completely formed? What would it look like, Brianna? My velocity profile. Well, where would the fastest speed be? In the middle. And it turns out that it's a parabola. Okay? The flow is parabolic in terms of its velocity in the r direction. Okay? So this is what we know as a fully developed velocity profile. So that's what happens when a flow goes into a pipe. Now, there's a couple of things you should keep in mind. For distances down the pipe, and remember, down the pipe in the axial direction is x. For distances where x is greater than x f sub h, oh, I'm sorry. This is FD. I forget my D. Fully developed. So this is x, FD, comma, h. All right. For distances where x is greater than the entry length, we consider the flow to be fully developed. And that has special significance, which you'll see in a moment. And when the flow is fully developed, there are some assumptions that we can make. First of all, all of the flow, we say it when the flow is fully developed, is in the x direction. Okay? So there's no flow in the r direction, or so therefore v is equal to 0. We also say, and this is very important, we don't say, we'll show, that du dx is equal to 0. Now what is that, no, not, Monday morning, not du dx, partial, delta u dx, delta. Partial of u with respect to y, or with respect to x is equal to 0. What does this mean mathematically? What does this mean in terms of reality of our viewing the flow?
It has a steady flow.
It has to say what?
It has a steady flow.
Close to it.
It's constant.
This shape does not change once you get fully developed. So the profile does not change once you get fully developed. Okay? And that's the significance of this. So in the fully developed region, u is equal to a function of its radial position only. So that's rather important. All right, before we get any further along, let's take a look at the Reynolds number. Now, of course, you're familiar with the Reynolds number already. We're going to use a variant of the Reynolds number, which you have seen before. Before you've seen the density rho, u, m, and I'm going to talk about that in a moment, over delta, or times delta over u. All right, where d, not delta, d is equal to 2 times r sub 0, where the diameter of the tube, and is equal to the mean velocity. We need to figure out what the mean velocity is represented by the velocity profile of the curve. And we're going to do that today. All right. If the flow, I should say, is considered turbulent, tube flow is considered turbulent if the Reynolds number is greater than or equal to, anyone know?
35.
No?
Isn't it 3,500?
No?
2,300?
What? Do I have no? 2,300. Although, that number is a little up for grabs. Some authors will say 3,000. Okay? But 2,300 is what we normally consider. Now, I will have asked and will ask before, calculate the Reynolds, calculate the hydrodynamic entry length. Open your textbook right now. Okay? Look at equation 8.3. This is an equation that you should have highlighted. Okay? Equation 8.3. A laminar flow, that is Reynolds numbers greater than or equal to, or excuse me, less than or equal to 2,300. I guess I better eliminate that. The hydrodynamic entry length is equation 8.3. If the flow is greater than 2,300, in other words, turbulent, isn't an exact expression that is accepted by most people, by a majority of people. So the author of this textbook has said, by and large, it's 10 times the diameter. Okay? It's 10 times the diameter for turbulent flow. All right? And that is expressed in equation 8.4. So, your entry lengths now you should highlight these and put them in yellow because I have on many occasions asked people to solve for the hydrodynamic entry length, and you can't do it if you don't recall where these equations are. Okay? And I will tell you one thing, things don't work right in the entry length. Most of the equations that we have, remember this when we get to heat transfers 2 or 3 weeks from now, and we do the heat transfer lab. When you're doing that lab, a part of the problem is that the equipment has such small, it's so small that we never really get out of the entry length in some cases. And things, the equations, the empirical relationships don't operate very well on the entry length. We've discovered it. Okay? So it's nice to know if you're operating in the entry length. All right, so now let's talk about the mean velocity, because that's one of the things we have to solve for. All right, we know that m dot, the mass flow rate, is going to be equal to the density times the mean velocity of the fluid times the cross-sectional area of the tube in which it flows. All right, you've seen this relationship before in this course, and you probably have seen it in fluids as well. Or we can say that mean velocity is equal to m dot divided by rho AC. And that is simply equal to m dot divided by rho, and now I'm going to take the area and I'm going to express the cross-sectional area in terms of the radius. Well, what is that? That's, pardon me? Pi r squared. All right, so now we have an expression for the mean velocity in terms of the mass flow rate, rho, and pi and r0 squared. And we're going to have to integrate this. We're going to have to integrate this over the flow of the pipe. So let's take and say this is our pipe, and this would be r sub 0. Okay? And we want to integrate this over the pipe. And if we take a small section, this would be 2 pi r, and this would be dr, the small area in there. If I want to integrate it, it would look like this. Um is going to be equal to 1 over rho pi r0 squared, which is the total area, over which I'm integrating, so I'm going to divide that back out. And I'm going to integrate over the entire area of the pipe from 0 to r sub 0. And it's going to be rho u, and here's our variable because u is constantly changing, as you know, times dA. Now we can express dA as follows. is equal to 1 over rho pi r0 squared times the integral from 1 to r0 times rho u. And now dA is going to be equal to pi times dr, or 2 pi. Pi r dr. Okay? Or, when I cross some of these things out, pi's, rho's, I end up with the following relationship. My mean velocity is equal to 2 over r0 squared times the integral from 0 to r0 of u times r times dr. All right, that is equation 8.8. All right, so now let's solve that. Well, let's take a look at the governing equations and solve for the velocity profile in the fully developed region. Okay, the first thing we're going to take a look at is our governing equations. We're going to look at the conservation of mass, or the continuity equation. And that is going to be and we're going to assume, incompressible flow, constant density, fluid of constant density. So we're going to divide out the densities. And for geometry of this nature, we have partial of u with respect to rx plus 1 over r times the partial with respect to r of r times v equal to 0. That's a continuity equation, and the momentum equation. In the, is u times the partial of u with respect to x plus v times the partial of u with respect to r equal nu over r times the partial with respect to r of r partial u with respect to r minus 1 over rho dt dx. dt dx is the pressure gradient, and that's constant. Okay? All right. Now, let's solve for u. We solve for u a function of r, then we can come back here and we can put u a function of r into that equation and solve for the mean temperature.
Is that the new?
This is new. Kinematic viscosity. Okay? All right? So let's solve for this. All right, let's first of all take a look at the continuity equation. Okay, and before we begin any further, let's remember what we're going to be dealing with. We're going to be looking for the I better add that. We're in the fully developed laminar region. Okay, we're going to be in the fully developed. Yes.
Is that the partial derivative of p?
These are all partial. No, this is not. This is total derivative of p with respect to x. It's the pressure gradient, and it does not change as you move down the tube. Okay? Talk about that a little bit more in a moment. All right. So we're looking for the velocity, the velocity profile in the fully developed laminar region. Okay, this is for laminar flow. All right. First of all, the continuity equation. All right, now we already hit on some of those things over here on the first board. We said in the laminar flow, in the fully developed region, we said V is equal to 0. Okay? V is equal to 0. So if I take and write my continuity equation, if V is equal to 0, what goes away?
Second part.
And, well, hang on before I do that. V is equal to 0, I said what else? That my profile does not change as you move down the pipe, right? So let's get rid of this term first. There's a reason behind that. All right, so now we can multiply both sides by, r, and what are we left with? We're left with this expression right here. Partial of this with respect to r is equal to 0. So what does that mean? It means that this could be RV could be equal to a constant. Now we're not saying what that constant is, so we'll call that C1. Okay? We're going to show that it's equal to 0. Okay? All right? And then we have two boundary conditions. Or excuse me, one boundary condition. And the boundary condition is that R equal R sub 0. We know that V is equal to V sub 0. Or V is equal to 0. All right, if that is the case, then what must V be everywhere, regardless of what the value of R is? must be what, Scott?
0.
It's got to be 0, and that's where that statement over there came from. So then V is equal to 0 everywhere. So for fully developed laminar flow, V is equal to 0 everywhere. In other words, flow is only flowing actually, it's only flowing along the axis of the pipe. All right. So V is equal to 0 everywhere. Okay? Now let's look at the momentum equation. All right? So we have U times the partial of U with respect to X plus V times the partial of U with respect to R equal, equal nu over R times the partial of U with respect to R plus, minus 1 over rho dP dx. Pardon me? Oh, yeah. Thank you. Sure did forget that. Thank you. Would have made a little different result. Okay, so let's take a look. Is U equal to 0? Now, what do we know about U? It's got some magnitude if you got flow in the pipe. What about the change of the profile of U in the fully developed region?
There is no.
There is none, so that's equal to 0. What about B?
That's 0.
That's 0. And we're not saying anything about the change in U with respect to R, because in fact we know that U does change with respect to R. But V is equal to 0. And therefore we're left with the following relationship. And now I'm going to multiply through by rho, so I'm going to have mu over R times d dr times r du dr, and that's going to be equal to dP dx. Did I do that right? Because nu times rho is equal to mu. All right? And this is equation 812. Okay? Now keep in mind what we're trying to do. We're trying to obtain an exact relationship for u, a function of r, so we can go back over here and solve, put that into here, integrate it, and come up with the value for the mean velocity. After all this work too, by the way, when you see the result, what it turns out to be. Anybody know what u mean is? All right. We'll figure it out in a second. All righty. All right, now we're going to separate and integrate.
It's going to be like a half or a third or something.
This spells it simply. Now we're going to separate and integrate. So we're going to multiply both sides by mu over. We're going to separate. Where am I? We're going to have d times r du dr. Why, by the way, did I change it from partial derivative to total derivative? Because u is a function of what? Only r. Okay? going to be equal to r over mu dp dx dr. All right? And that's going to be equal to r du dr, and that's going to be equal to 1 over mu dp dx times r squared over 2 plus c1. Now I'm going to divide through by r, and I'll have du dr is equal to 1 over mu dp dx r over 2 plus c1 over r. Yep. Okay, now separate and integrate again. We have du equal to 1 over mu times dp dx r over 2 dr plus c1 over r dr. We integrate, we end up with u, a function of r, equals 1 over mu times dp dx r squared over 4 plus natural logarithm c1 times the natural logarithm of r plus c2. All right. Now we need to apply our boundary conditions. All right, boundary condition number 1. At r equal r sub 0, what is u?
U infinity.
What?
U in,
0.
0.
Zero.
Sorry.
That's the, what do we call it? The no-slip condition. In other words, it's stuck to the side. Anybody know what the second boundary condition is?
At the center.
Yeah. At r equals 0, what?
U infinity.
Nope. No, u is not equal to infinity. But that would be a strange
The
thing.
change in the derivative is 0.
The change of u with respect to r is equal to 0. That's a symmetry condition. And these two conditions, when it comes to pipe flow, you'll see again and again. You have the no-slip condition, you have the symmetry condition. All right? So, though, with those two conditions, we can apply the boundary condition. All right, if we apply boundary condition number 2 first, to this right here, this expression right there, what do we have? We have at r equals 0, so this is equal to 0, this is equal to 0. What's du dr?
0.
Equal to 0. So what's c1 have to be equal to?
0.
0. All right, so C1 goes away. We'll now apply boundary condition number 1. All right, at r equal r sub 0, u equals 0. So this side will be 0, this will be r sub 0, and C2 will still be there. So what will C2 be equal to?
Negative 1 over mu.
Right, minus 1 over mu dp dx times r sub 0 squared over 4. All right, now let's put those all together, and we end up with the following result. U, a function of r, is equal to minus 1/4 mu times dp dx times r sub 0 squared over, or times 1 minus r over r sub 0, and that quantity squared. And that is equation 813. All right. Okay. And now we have to now we're going to solve for u max. Okay. Where will u max be? In the middle.
How did we figure out that C1 was 0?
How do we equal? What do we do?
For C1, how did we figure out it was 0?
We applied boundary condition number 2 to this equation right here. R is 0, du dr is 0, so the C1 must be equal to 0.
R0 for them?
Boundary condition number 2. At the center, r is equal to 0, the center line. R is equal to 0, and that point, du dr, is equal to 0 because that's a symmetry condition. Okay? I can't see it. It's kind of weird. Ties heads on your body. You seen that new Snap? What is the face swap? My son is doing that all the time. You know, we were at brunch yesterday, and my 5-year-old. So that's our u max right here. All right. So now, and the pressure gradient, by the way, is negative, so it turns out to be an actual number. All right. So what does that mean? What that means is, so u, a function of r, is equal to the maximum velocity times 1 minus r over r sub 0 squared. And that is the expression that we have for u, a function of r. Okay? So now we go back. And we have equal to 2 over r0 squared times the integral from 0 to r0 of u, which is u max, times 1 minus r over r sub 0 squared times r dr. And if we do that integration, u mean turns out to be the maximum velocity times divided by 2. All right, and not quite done, close, but not quite. We can also say then that you at any point will be equal to 2 times the mean velocity times 1 minus r over r sub 0 squared. And this is equation 815. Where do you think we measure when we stick a sensor into a pipe? Where do we measure the velocity?
Q max R0.
Yeah, and you divide by 2. All right. So your mean velocity. That's typically where we measure when we put a sensor into a pipe. Now we're going to use this equation in next class, because in next class what we're going to do is something a little more interesting, because this has only been fluid mechanics. What we're doing next class is we're going to come up with the formula for the temperature and ultimately the heat transfer coefficient for flow in pipes. But as much as we can get into today. Before we leave though, I have one last thing I want to leave you with in the last 2 minutes. Your homework, I thought about giving you another derivation, but I thought, I think you're sick of the derivations. And I thought I'd give this back and then everybody would be annoyed, and then if I gave you another derivation, you'd get really annoyed, okay? So, trying to be sensitive to the feelings of my students. It's not easy. 8.1, 8.2, and 8.3, parts A and D only. You don't need to do the graph, okay? You don't need to do the spreadsheet and graph. Okay? Now, it doesn't get easier in a chapter than the first 3 problems, all right? But in order to do these problems, you need to take a look at the pressure gradient. Well described in your book. We need to talk a moment about the pressure gradient. Pressure gradient being TVDX. The first thing that you're going to look at is the Moody friction factor. This is all in your book in last night's reading assignment. That is F, is described as being equal to minus dpdx, the pressure gradient, times the diameter over rho times the mean velocity squared divided by 2. Okay? So laminar flow F turns out to be equal to 64 over D. That's equation 819. So for laminar flow, that's pretty easy to do. For fully developed flow, for fully developed turbulent flow, you've got 2 choices. One is a regular pipe, and you can use the friction chart, the Moody chart, or you can use equation, which I want you to use this time, equation 820. And there's a line on the chart for smooth pipes. By the way, what's the smoothest pipe in the world? What? What's the smoothest pipe in the world? Hands down. Not even close.
Gold.
What?
For equation 819 in the book, it's 64 over the Reynolds.
Well, oh, I'm sorry.
Good try.
64 over R.
There's nothing to solve.
Oh, I'm sorry, I miscopied. You're right. No. What's the smoothest, not even close. What's the smoothest material in the world? Smoothest pipe?
Glass.
Your blood vessels. Your muscle is your pump. Your heart is your muscle, which is your pump. Think about the amount of fluid it pumps every second through your body. The frictional drop in your veins and in your arteries is next to nothing. What was the biggest part with the artificial heart when they had it? Kept getting blood clots. Because no matter how smooth they made the inside of that, when compared to a blood vessel or an artery, it was very, very rough surface. Anyway, I'm running out of time. Dr. Stein is probably standing outside and he gets very antsy. Equation 821. And I will point out that equation 822A shows you the pressure drop. And equation 822B talks about the pump power that you need for a given pressure drop. You're going to need both those equations to solve these two homeworks. Okay? Any questions?